formula, Macdonald polynomials.
Thank you. Thanks to the organizers for giving me this opportunity. So this is joint work. I'll mention joint work with Olia Mandelshtam, who's now in Waterloo, and James Martin from Oxford. And this is a new formula for the modified Macdonald polynomials. So one of the advantages of being the last speaker is, of course, that you can make use of the fact that previous speakers have defined everything for you. But one of the disadvantages in a regular conference is that, of course, Friday afternoon, people have already taken off for their extended long weekend. I don't know what the ramifications of such a thing will be in an online conference, but thanks to, and I agree with Gaurav completely, thanking Venkatesh for organizing this wonderful conference. And in particular, I learned a lot from the very nice talks so far. Okay, so here's the outline. So I'll first motivate why we wanted to study, wanted to get a new combinatorial formula in the first place for modified Macdonald polynomials. In particular, I'll mention two motivations that led us to these formulas. There will be an interlude on this kind of new interacting particle system for this community. I mean, although this was known before, I think it has not received the kind of attention that it maybe should. And then I'll mention some ideas of the proof for the combinatorial formula, and in the part of the proof is proving some very nice generating function identities for words, which is basically Q series. So since Gaurav is the organizer, I mean, I hope that this will make him happy. Okay, so let me begin with the basics. I mean, I guess I don't have to dwell too much on them. So we have a family of commuting indeterminates, x1, x2, etc. And if you work with the algebra of symmetric functions, with rational coefficients, then there are several natural bases, monomials, the elementary symmetric, homogeneous, and the power sum. And of course, the one ring to rule them all are the Schur functions. This is all well known. And the Macdonald polynomials, so now we lift to coefficients which are rational functions of two parameters, two other independent parameters, commuting parameters to t, and then you have an amazing family of symmetric functions indexed by partitions called the Macdonald polynomials, and these are the simultaneous generalization of the Schurs, the Hall Littlewood's, and the Jack polynomials. Of course, they have other motivations as well. And just for completeness, I will recall the standard inner product on this space. Which is defined in terms of the power sum symmetric functions. And Macdonald's famous theorem is that these p lambdas are uniquely determined by these following conditions: that they have a monomial expansion in terms of partitions which are smaller in dominance order, and with the leading coefficient being 1, and they are orthogonal with respect to this. Okay, so this everybody knows, and so the modified Macdonald polynomials were obtained by Garcia and Heyman by a plethism of the integral form, the scalar multiple of p lambdas. And I think Anton Mellet defined it. So this is the first of those definitions that I will make. And they are, again, I mean, Garcia and Heyman translated Macdonald's axioms for the modified Macdonald polynomials, and in this plethistic notation, they satisfy these three conditions. So in terms of the Schurs, when you have this extra family of variables involving the t's, then you have this condition where the mu's are greater than or equal to lambda prime, conjugate. And if you have the q, then it's mu is greater than or equal to lambda. And the inner product, the same inner product that I defined earlier, has this condition. Okay. So Hagelin, Heyman, and Ler gave a combinatorial formula for this H tilde lambdas, and this paper has been sufficiently, has been mentioned so many times in this conference already that I shouldn't spend too much time on it, but I will give some ideas of the proof. Okay, so other combinatorial formulas which are relevant to this talk is a formula. One is a formula by Corteel, Mandelshtam, and Williams for the Macdonald polynomials, the usual Macdonald polynomials, in terms of what are called multiline queues. So these were, I'll say more about them later, but these are objects that were introduced by Ferrari and Martin to understand the stationary distribution of an exclusion process, a different kind of interacting particle system than the one I'll focus on. But this is the one that, for example, Luigi mentioned in his talk. So Corteel, Hagelin, Mandelshtam, Mason, and Williams gave a formula for the modified Macdonald polynomials as a sum over tableau, similar to Hagelin, Heyman, Ler, but this time they had fewer terms, and this is the work that we will build. And I just mentioned in passing that Garbali and Wheeler gave a different formula, different combinatorial formula for the modified Macdonald polynomials, this time using some colored vertex models. Okay. Of course, there are many other formulas, so I'm not describing those. So in this third paper over here, these authors conjectured yet another formula for H tilde for the modified Macdonald polynomials using the match statistic and a new statistic that we are calling q-inv, and I'll explain a bit of this why. So the first motivation for us is to settle this, was to prove this formula, and that's what we did. The second motivation comes from the following question. So, as I mentioned, the objects describing the stationary distribution of the ASEP, multispecies ASEP, were used to give a combinatorial formula for the usual Macdonald polynomial. So it's natural to ask if there is another particle system for which the combinatorial gadgets describing them could be used to compute the modified. And so we show that there is a stochastic process which I'll describe, whose stationary distribution can be computed in terms of, sorry, forget this word, in terms of this tableau, at least when q is 1. Okay? So these are the two main motivations. Okay, so now let me set out some notation. So lambda is a partition in weakly decreasing order. So unfortunately, or fortunately, there is yet another notation for partitions thanks to Hagelin, Heyman, Ler. I mean, this is none of the usual notations, so maybe we should call it, I mean, we already have the British, French, and Russian notation. Maybe we could call this the American notation. So this is the, I mean, it's the conjugate in French notation. So what you do is you draw the column. So the ith column contains lambda I boxes justified from the bottom. Okay. So the diagram for 3, 3, 2, 2, 2, 1, 1 is this. So you count like this, not like this. So it's a bit confusing, but they have set the notation. We have to follow. Okay, so tableau, as usual, is a filling of these cells, and okay, again, ignore this word. It's just an arbitrary filling with positive integers, with no restriction on increase or decrease in any direction. So the monomial weight of a tableau sigma is just, we'll denote it x to the sigma, it's just x1 to the number of 1s, x2 to the number of 2s, etc. So in this example, it's x1 to the 5, x2 to the 3, and x3 to the 6. Yeah, as usual, please interrupt me if there are any questions. Okay, so this is the first statistic. This was already there in HHL, Hagelin, Heyman, Ler. So a descent is a pair of entries where pair of entries in cells, say u and v, where u is immediately above v, and sigma u is strictly greater than sigma. in which case, in that case, we say U belongs to the descent set of cells. So the leg of a cell, I mean, this is funny notation, funny terminology, I mean, is the number of cells above U. So it's, I find it strange to use the word leg, but you know, again, all the terminology has been decided by these three guys, so now we have to stick to it. So the leg is actually up. Okay, it's the number strictly above U though, okay? And the major index, just in analogy with permutations, the major index of a tableau is sum of all the cells in the descent of 1 plus the leg. So if you want, if you include the cell and add it to leg. So in this example, the descents are over here. I mean, I've marked them in red. So 3, 1, 3, 1, 3, 2, 3, 1, 3, 2. And the major index is 4 because this contributes 1. This contributes 2 because the leg is 1. This 1 and this is 1. Okay. Oh, sorry. So it should be 5. Sorry. I forgot my addition. Yeah, sorry. This is a typo. This should be 5. Okay. All right. So since I'm going to compare HHL and R formulas, I'm going to introduce some notation that's maybe not standard, but it will be maybe useful for visualization. So now I'm in the process of describing Hagelin-Haven-Lörs HHLs. So we say that 3 cells UVW in a diagram form a gamma triple if they are arranged as follows. So U is directly above V and W is in the same row as U. It need not be adjacent. It can be arbitrarily far away. And we say gamma triple because this looks like a gamma. And we also allow degenerate gamma triples where U and W are in the bottom row so that V does not exist. If you like, you can think of that as putting a row of zeros below the diagram. Okay, so a gamma triple forms an inversion if the entries in it, as you go counterclockwise, are in increasing order. Okay, so there should be some point of the counterclock of the circle where you start and you go. As you go counterclockwise, these numbers are increasing. If there are ties, then you break them by reading order, and the reading order goes row by row from top to bottom. Okay, so it goes like so. From left to right, sorry, I should stress that. That's important for us. It's going to be left to right in HHL. And for the degenerate case, it's just a regular inversion of permutation. So that is, the numbers are, the larger element is to the left. So here are some examples of inversion. So here you see you go counterclockwise, and these are increasing. This is also increasing in counterclockwise. So if you have distinct entries, exactly half of them are inversions and half are non-inversions. So these are going clockwise. So let me just give you one example of breaking the tie. So these two entries are the same. So you break the tie by reading order. So you assign this to be a 1 and this to be a 3. No, so then something is wrong. No, sorry. This becomes a 3, this becomes a 2, because you have to proportionately push everybody up. So this is 1, 3, 2, and that's the same as this. That's okay. And the general rule is if 2 entries are equal, then, I mean, the 2 entries U and V are equal, then you get an inversion unless the last entry is also the same. So this does not give you, but these two give. Okay, so okay. Maybe some of you know this already. So in the running example, so you get 7 inversions, and let me just illustrate with this pair of U and V. So if this is U and this is V, then this will give you an inversion. This will not give you an inversion because all 3 are the same. This and this will also give an inversion. So you'll get 3 inversions from this guy, and that's the 3 over here. And if you compute with everybody, you'll get 7. And if you let in sigma be the number of inversions, including degenerate ones, then you get, then this is their theorem that the modified Macdonald polynomial is given by the sum over all tableaux of q to the match t to the inf times the monomial. Okay, any questions so far? Okay, so now I'm going to compare with our formulas. Oh, sorry. Before that, let me just give you an example. So I take this is going to be my running partition 2, 1, 1, and let me take two variables. So I'm allowing all possible fillings with 1 and 2, and so the first tableau over here contributes to x1 to the 4, and there is there's no descent, and so no major index, and there's no inversion. And similarly for the other guy, similarly you can write down everybody. So let me focus on one example just to give you the idea. So there are no gammas here, you can see. So there's nothing where there's no non-trivial element on the second row. There's no W on the second. So the only inversions come from the degenerate ones, in which case there's one inversion from this 2, 1 in the bottom row. And you get major index contribution 1, so Q to from here, so Q to the 1 and T. And this, if I sum all these guys, I get exactly the expansion of the modified Macdonald. Okay, so now I want to introduce this new statistic, and this is where things start to look very, very similar to the HHL formulas, but they're not. And non-trivially, they're not. So now we say that three cells form an L triple, not a. So you flip the gamma, you get an L, where you have three cells arranged as follows. So U and so V is directly below U, and this time W is in the same row as V, but can be arbitrarily far away. Okay. And again, there's the notion of a degenerate triple, and this is the case where you are in the top row and U does not exist, but you have to be in the top row where columns are equal, of equal length. You cannot be in a top, I mean, it's not allowed for W to be the top row of its column and V to not be its top. Okay, that's not allowed. So these V and W have to be the top rows of their columns of the same height, therefore. And this you can imagine by putting infinities on top of the diagram. So you just decorate your diagram with a bunch of infinities on top. So that will equivalently give you this L triples. And we say these L triples form a Q inversion if the entries increase as we go counterclockwise, again as before, as in HHL. Now the ties are broken by reading order, but for us now the reading order is row by row. But within each row we go right to left. So we read in Hebrew or Arabic within each row. Okay. And again, I give you more or less the same examples as before. So these are Q inversions, and these ones are not. So if all are equal, you don't get a Q inversion. And if two are equal and on the same, if two are equal, you get an inversion if and only if they're in the same column. Okay, so similar. And now for degenerate triples, which are cells, two pair of cells on the top row, you get a Q inversion if these cells form what sometimes called a co-inversion. I know Arun does not like this terminology, but so they are in the right order, if you like. So just like the identity permutation gives you the maximum. Okay, so again in our running example, you get 12 Q inversions, and you take this. For example, I explain this 1, 1 again. So now I look at and the W's come from the bottom row, and this does not give me, this gives me, this does not, and the other three do. So I get 4. Total is 12. And so q-inv for us is the number of Q inversions. And you might ask why q-inv? I mean, what's the why this funny terminology? And the reason comes because because we'll have some queuing processes behind in the back of our mind. So the Q here is a homophone for the Q, a line or a Q. So okay, so our theorem, which was conjectured in this paper by these people, is that the modified Macdonald polynomial is given by the sum over all tableau, same kind of tableau as before, q to the match and t to the quin. So it's a bit unfortunate, but the q in the quin comes with the t. And x to the sigma. Okay, so this is our theorem. And you can see the striking similarities between both these kind of formulations. So these two statistics are...
May I ask a question?
Yes, please.
So just to clarify, is it possible to describe those sigma which have this q u inf being 0? So what are the 0 values?
Yes, I believe there is a classification, but I have suddenly forgotten.
So in other words, is it possible to say what is t equals 0?
Yes, I understand. Yes, it is possible. It's a bit tricky. Or maybe not. I've forgotten. Yeah, it is possible. It might be there in our paper.
Okay, thank you.
Yeah. So it's very similar in spirit to HHL. So do you know the answer for HHL? That might jog my memory.
Well, I think for HHL, they should be somehow increasing in columns maybe or something of this sort, but
right.
I don't know.
There is some such thing. Yeah, I think that's correct. Yeah. So
thank you.
In particular, they are equidistributed, right? So the sums are the same. Both are equal to the modified Macdonald polynomial. So the t power 0 terms are, will give you the same same generating function, right?
I see.
Yes.
But can I ask also? So
sure.
If I understand right, it's still exactly the same as Hagelin, and Lohr if the columns are different.
Right. Yes.
Is that right? Yeah. Okay. Okay.
I'm going to say that our proof simplifies significantly in that case. All the non-triviality of our work is essentially in the case where we have repeated parts. So if lambda is a strict partition, our proof more or less tracks HHL's proof. Yeah. So as I said, well, the when q-quin statistics are very similar, that we don't see any simple way to go from one to the other. In fact, at the end, I will mention some more refined conjectures, which we also do not want to prove. And so it seems like there should be a nice projection explaining this, but we don't see it. But this, as you know, this is frequent in Macdonald theory. Identities that come down from Macdonald. Okay, so let me compare the two formulas for the same example. So in red, I have written the HHL formulas, and in black, our formulas. So of course, in the trivial cases, they are both the same, but you see, even for like x1 cube, x2, you see that these two are different. They don't match here and here. They do match here and here, but in some other cases, they don't match in an obvious way. There's some cyclic action. It's not like there's some involution that will give you quality. And so let me compare with the same example. So remember, for HHL, there were no non-degenerate or non-trivial gamma triples. For us, there are. Potentially, at least not here, but there could be. So here you get q to the 1 again because the match is the same, and t to the you get t to the 0 y because in this L triple, for example, two are equal, but they are not in the same column, and ditto for the last one. And this does not contribute to quin because it's in the wrong order, so it does not give you a co-inversion. Okay, it is an inverse, so you get a t to the 0, but the sum is still the same, and you get the modifier. Okay, so now let me come to this this interlude. So maybe there are not many probabilists here, so maybe let me just quickly mention what zero range processes are. So these were first defined by Spitzer in this influential paper from 1970 where he defines everything from exclusion processes to zero range processes. So these are, again, we will think of them in continuous time. These can be potentially defined on any graph, and you could have some extra data. You could have like sources and sinks, for example. We will only work with the graph, which is the ring on n sides, so Z mod nz, if you like. And in its simplest formulation, there is only one kind of particle, and there are, let's say, k of them. And configurations for us will be absolutely any assignment of particles on the sides. So there could be no particle at a site, there could be 1, 2, 3, any number unbounded. So there's no restriction whatsoever. Okay. And so for us, we will consider, so this is an interacting particle system, so it's a Markov process. And so particles will be hopping around. For us, we will think of particles moving counterclockwise. And so if you, for example, so if you write it in one line, particles will move left. Okay. And the big theorem in zero range processes is what I'm going to define now. It's due to Spitzer already. So suppose f is any function from the non-negative integers to the positive reals such that f of 0 is 0. So then we define transitions as follows. So if you have a site, let's say, oh, sorry, there's a typo here. Okay. So if you have a site with J, with, if you're sitting on site I with tau I particles, then a particle from the top will move left with rate f of tau I. So the J, this J should be an I. Okay. So in other words, the rate of hopping of this particle it only depends on the information at that site. So the fact that you had J particles, oh sorry, tau I particles at that site determines the rate. I don't care what's in the rest of the world. Okay. So so at the origin, so that's why zero range. So it does not have any dependence on things outside of your own site. And the main interest in these processes comes from the fact that no matter what your f is, your stationary distribution will always be a product measure. So in other words, for any configuration, tau 1 to tau n, the stationary probability will be proportional to a product of g of tau 1 up to g of tau n, where g is some other function. It comes from f, of course, but it's not f, and it's not like immediate how to get it in some cases. So you have to do something.
Sorry, I'm sorry. Do you fix f or it's changing?
Sorry, no, f is fixed. So
okay.
So if you had 3 sites, then the particle would hop with rate f of 3, and if you have 2 sites, it would hop with f of 2, and so on. Okay. That f.
And may I ask one more question? So is the process discrete or continuous?
No, I said it's continuous time. And you can define it in discrete time. It's more natural in continuous time because you want only one particle hopping at a time.
Thank you.
Yeah. Right. So so this is all old stuff. I mean, it's known since the 70s, and physicists have used this a lot. But we came up independently with this multi-species version of this, and it turns out that so after we kind of found it, we found that this is already in the literature. So mainly the group of Kuniba, Maruyama, and Okado in Japan have been studying these processes for a while, starting around 2015, and they published a review in Sigma in 2017. So if you want, you can take a look. And there are versions of increasing complexity. You can have one particle jumping, many particles jumping. Rates can be complicated, but all of them are motivated by integrability. So they always satisfy Yang-Baxter. So that is their motivation. So we first realized that it's a special case of one of their models some time ago, but then we realized, or rather James found this reference by Takayama, which is only on the arXiv, where he studies more or less exactly our up to some maybe change of notation. So the credit for discovering this particular nice model goes to him. He did not realize that the modified Macdonald polynomials are playing a role. Okay, so let me describe the process. So again, you fix a partition. Okay, there's another typo here, close parentheses, of positive integers. And so lambda I will denote the number of particles of species I. Okay, so there are different kinds of species of particles. And okay, so maybe I'll come to that later. And in frequency notation, let MR be the multiplicity of of species R. As before, we have n sites. So the sum of the lambda i's is n. And now for us, a configuration, again, tau, which is tau 1 through tau n, is a multi-set composition. So it's a composition where each part is a multi-set. And rather than getting into technicalities, I'll just give you an example. So let's take my same old lambda with n equals 2. So you have one particle of type 2 and two particles of type 1. And you have two sites. So these are the 6 possible configurations. So you can have all 3 on the first site, nothing on the second site, both the 1s on the first site and 2s on the second, and the 2 on the second site, and so on. Notice that the 1s are indistinguishable. So I do not distinguish between this one here and this one. Okay? And here also, I mean, there's no ordering. I mean, so that's why it's a multi-set. I don't care. 2 1 1 is the same as 1 2 1. Okay, so this is the kind of configurations we have. And just like in the usual zero-range process, for us, every transition will involve a particle jumping from site j to j minus 1. Okay, and so what does multi-species mean? I mean, what distinguishes the two species? So for those of you who know the ASEP, you might know this already. So we think that some particles have higher priority than the other particles. So the ones so in our notation, we'll think of ones as the strongest particles. Somehow, sometimes called first class particles, and 2 being second class particles, and so on. So the first class particles are privileged, just like maybe in ordinary life. So they get the first chance to go. And if perchance they don't go, then number 2s get a chance to go. Okay. And there's a global parameter t, which we should think of as less than 1 from the point of view of the process. Of course, everything is formal, so we don't have to worry too much about it. And we also have site-dependent, these so-called inhomogeneous parameters, x1 through xn, just like we had in Joule's talk. So, and also in Luigi's talk. So, maybe, but in a different way. Okay, never mind. So now here is the rates. So fix a site j. Now for every a, you have an exponential clock with index a, which rings with this rate. So 1 by xj t to the a minus 1. So for example, the topmost particle hops with rate 1 by xj. The next particle hops with rate t by xj, and so on. So that's why you should think of t less than 1, because the first particle is the strongest. Okay. Now, if j has less than a particles, then nothing happens. I mean, if your a is too large, if your clock rings for a large a, then you don't care. But otherwise, the ath highest particle is going to jump. So, because we have particles repeating at sites, what does this mean in practice? So here's the interpretation. So suppose we are fixing j, okay? We are at site j, and suppose there are c particles of type r, and the number of particles of type greater than r is d. Then the rate is proportional to t to the d times the c integer, or t integer of c. So for example, c subscript, box c subscript. Right? So this Q series notation. Okay. So here is an example to illustrate the rates. So suppose let's look at this side, this configuration, same partition but on 3 sides. Then the 2 can hop with rate 1 by x3 because it's the largest. This one can hop with t by x3 and this one can hop with rate t squared by x3. But the effect of either of them jumping is the same. So you add the rates. Okay, this is a standard computation from exponential random variables. So you get this kind of prefactor. Let's look at this other example. So here from the first side, or let's look at the last side first. This one will hop left with rate 1 by x3. This 2 will hop left with rate 1 by x1, which means it will go to the last side because remember we are on the ring. And this one will hop left with rate t by x1. Okay, so these are the rates. Are there any questions about the rates? Or the process in general? Okay. So for example, here is so I'm recalling the elements of the state space. This is a finite state space Markov process, so there's no problem really. It's easy to see that you can get from any side to any other side. So it's an irreducible process. And so you write down the generator, which is, so the generator for us, I'm using physics notation, so it's column stochastic. So the ijth entry is the rate of going from j to I, not I to j. And on the diagonal for j not equal to I, and on the diagonal you put something so that the column sum is 0. And then if you look at the right eigenvector in the kernel, there should be a unique one, and that's going to be proportional to the station. So that's how you actually compute it in practice. Okay.
Sorry, may I ask a question? Is it obvious that the matrix is column stochastic? I mean, in this example, it's clear, but is it obvious in general?
No, you construct it that way. I put the diagonal entries to be negative of the sum of the other.
Oh, I see. Thank you. Yes.
And then all you need to do is to look at the right eigenvector in the null space. And there's a unique one by irreducibility. Okay, so now how is this related to these tableaux? So now let me describe a projection. So suppose sigma is a tableau. Let's go back to our tableau. We are going to associate to every tableau a configuration in this TAZRP, in this mTAZRP as follows. So rather than defining it, let me show you how it is in this example. Again, my favorite example. So you look at the bottom row, okay? And so the bottom rows mark the positions where the particle of type equal to the height of that column will sit. So this has height 2 and this column has height 2 and the bottom location is filled by a 2. So the 2 is in the second side. I apologize if that was too full of 2s. We can do another example. So look at this height, this column, it has height 1. Its bottom entry, which is its only entry, is filled by a 3. So there is a 1 in the third side. And similarly, there's a 2 here. So there's a 1 in the second side. Okay. And so the only tableau that map to this state are these 6 ones. Because you need to have a 2, 3, 2 in the bottom or a 2, 2, 3. Both are allowed. And the top can be a 1, 2, or 3. Okay, so these are this. So this is the projection. And so our theorem says that the stationary probability of this configuration tau for this mTAZRP is going to be a sum over all sigma which project to tau of t to the quin of sigma times the monomial weight x to the sigma. And the normalization factor is precisely the modified Macdonald polynomial at q equals 1. and that is the partition function. Okay. And again, we are running over all tableau, but now we don't allow all tableau. I mean, we want a finite state space. So we only allow entries in 1 through n, where n is the number of sites.
Sorry, can you say a few words? What do you mean by stationary probability of this state?
So, okay. So in probabilistic terms, it means that when you start this process, it's a stochastic process. So there'll be random hops all over all the time. And if you wait long enough, you can ask what's the probability for any fixed state. Okay. And that is given by this quantity over here. And as I said, in response to your earlier question, in practice, it's just a linear algebra problem. You have to find the eigenvector, right eigenvector, with eigenvalue 0 of this matrix, such a matrix, of the generator matrix.
And what is your starting point?
It doesn't matter.
Oh.
Right. So irreducibility and some other, well, we are in continuous time. So irreducibility will guarantee that your initial conditions are washed out. Okay.
Yes.
And you're also guaranteed that this vector will be a vector of strictly positive entries. I mean, we are assuming all these parameters are real positive. Okay. So then you will have strictly positive entries, and so you can normalize them to make them a sum to 1. So you get an honest probability distribution, and that's precisely what this is going to be.
Thank you.
Yeah, that's a very good question. Yeah, maybe I should have said that earlier. Okay. All right. So the idea of proof. So if you recall the multi-species ASEP, like in Luigi's talk, as I said, the formula for the stationary distribution was established by Ferrari and Martin. They used these multi-line queues, and then they constructed a stochastic process on these queues, which projects onto the multi-species ASEP itself as a projection of Markov chains. And we will do a similar thing. This time we will use a multi-line process. So it's like a multi-line queue, but each side can have more than one particle. So each row is like a multi-line, each row is like a zero-range, multi-species zero-range process. And we do something more. We even get an enriched Markov chain on tableau, these things. But I should stress that we are not able to insert the q. So we have q equals 1, and there are lots of nice things that happen for q equals 1. I'm going to say some things more about it, but we're not able to get something for general q. And this Luigi also mentioned something similar for the multi-species ASEP. Okay, so let's give a sanity check of this formula. So remember that from the point of view of the multi-species TAZRP, it only cares about the order relationship among the species. So if you have species 1, 2, and 3, it's pretty much the same as having species 2, 17, and 23. I mean, how does it matter? I mean, 1 is better than 2 is better than 3. So that's all that it cares about. But the partitions are going to be very different. And so you're going to get something much more complicated for this example rather than this example. Okay. So for this result to be true, we would need, at the very minimum, we would need that the modified Macdonald polynomial indexed by the partitions involving 1, 2, 3 should divide the partitions indexed by 2, 17, and 23. You would have to have that. If that's not true, then this cannot possibly be true. But this happens for us because the modified Macdonald polynomial has this identity when q equals 1. It can be expressed as a product of column H tildes for column shapes. So, and given by this precise formula. And so if you write your partition frequency notation, like I to the m1, I1 to the m1, I2 to the m2, etc., where I1 is less than I2 less than Ij, and you write mu by replacing I1 by 1, I2 by 2, etc., then we do get for free by this identity that h tilde lambda is divisible by h tilde of mu only when q equals 1. So this breaks down when q is arbitrary, and that is one of the obstructions in figuring out the combinatorials. Okay. So just to give you an example, here are the numerators of the stationary probabilities for these 6 states in my running example on 2 sides, and if you sum them, you get exactly the so this squared comes from the fact that this is ones and this is a 2. Okay. All right. So again, just to illustrate the stationary distribution computation, so for these 4 tableaux which project to 2, 1/1, you have 4 tableaux on 2 sides, so you have n equals 2. And if you calculate their weights according to the formula I mentioned, you get the sum, which is this, which is exactly this one. Okay, so it all works very well. Okay, so how much time do I have, Gaurav? I think we started late, but I want to...
10 minutes for sure.
10 minutes?
Yeah. Okay,
so maybe I'll not spend too much time on the proof. Let me just say that the strategy. Okay, so we have, so let me define C lambda to be the sum, and I want to prove that C lambda is H tilde lambda. That's the idea. And so by the existence results of Garcia and Heyman, we have to prove 4 identities. We have to prove 4 things essentially. And we are following exactly HHL's strategy, as I said before. First, we have to show that it is symmetric. Then we have to prove that it satisfies these axioms. Okay, all these 3 axioms have to satisfy. Fortunately, axiom, the last axiom is trivial. I mean, it's just again for HHL it was trivial. So I have to prove axioms 1. I have to prove first symmetry, then axioms 1 and 2, and these are basically following HHL almost on the nose. And I again recall the LLT polynomials from Misue talk, and so you expand these C lambdas in terms of LLT polynomials of ribbons using descent sets. I mean, similar, exactly what she had in her talk. And for axioms 1 and 2, it's kind of the same. So I'm running out of time, so I would rather not dwell on them too much. For axiom 2, things proceed up to a point, but let me tell you where the complication is. Okay, so we end because, so recall that the degenerate inversions in HHL were all coming from the bottom row. For us, all the degenerate cases come from the top row, and so there are only problems. So there are only problems when there are partitions of repeated parts. So in that case, we have to do a whole lot of jugglery. We define some notion of distinguished cells and so on. Okay, I think I would rather not spend time on this, but we have to separate our tableau, or rather something called super tableau, into 3 cases, and what we end up showing is that this C lambda essentially contributes from only one of these cases, and that gives you the identity. And as I said, if lambda is a strict partition, we have no degenerate tableau, and then we are done. But we have to work much harder when they're repeated parts, and then we don't have a bijective proof. We can't give a simple involution, sign of a single involution. So the rest of the paper of about 16 pages spanning 3 sections is just involved in proving that case. And this reduces to generating functions for certain words, which I think, given that people like Ola and Michael and Gaurav are here, I would rather show you these nice identities. So these are generating functions of certain words. So so let me just set some notation. So let n be a positive integer greater than or equal to 3. And we have alpha 2 through alpha n minus 1 tuples of positive integers. And mod alpha will be the sum over these alpha I. And n is a large enough positive integer. And L will be the difference. So we are going to consider words of length capital N in the alphabet 1 through small n. Okay, such that the following conditions hold. So these W is a word such that there are exactly k capital N's. Okay, there are L minus k ones, and there are alpha I i's for the other I. Okay, so for example, so if we have words of length 3 in the alphabet 1, 2, 3 with L equals 2, that means I should have said maybe k equals, no, so k is varying, sorry. So k is the thing that's varying. Sorry, there are too many parameters, I'm confusing myself. So k is the parameter that's varying, k runs from 0 to 1. So for k equals 0, I have no 3's and 2 1's and 1 2. When k is 1, I have 1 2, 1 1 and 1 3, so it's permutations. When k equals 2, it's the other way around. I mean, it's the opposite of this. Okay. Okay, so again, co-inversion, I already said what this is. So co-inv of W be the number of such pairs. So now I define this new statistic, which is related to our quinv, and we call it quinv prime because it's on words. This is co-inv plus k choose 2 for a word in WK. Okay, so this is where the k is going to play a role. So the statistic depends crucially on the k. Okay, and now I'm going to partition my WK into 2 subsets with the superscripts less than or equal to and greater than. Definition a bit complicated. So for the superscript less than or equal to, these are words where the position of the leftmost n from the left is less than or equal to the position of the rightmost one from the right, but you ignore all ones in the right side computation, indexing. Okay. So here is an example. So for again in these cases, so okay, maybe I shouldn't do it on the fly, but just to show you, these are the words in where it's less than or equal to, and here it is greater than. And if I sum the quinv primes over these 2 cases, I get nice products. I mean, I get nice factorizations. It's not obvious from the definition. And so the theorem that we really need is that there is, so I define W superscript less than or equal to be the union of all those guys for all k, and similarly W greater than. And so we claim that there exists a bijection which from this set to this set, which maps WK greater than bijectively to WK plus 1 less than or equal to for each k, which respects the quinvs and which preserves the subwords in these other letters, except for 1 and 2. So let me go back to that first example. So here is W0, which is the same as W0 greater than, and you see the quinv primes are just the co-inversions because 0 choose 2 is 0. Here too the quinv prime is the co-inv because 1 choose 2 is also 0. So this is the standard co-inversions. for permutations of length 3. And I have split it in this way to show you that the statistics match. So there's 1, 2, 1, 1, and 1, 0 here, and this is also here. And here, here 2 choose 2 is 1. So here you're adding 1 to the co-inversion. Okay, so this is not the co-inversion anymore. All of these are co-inversions, not this one. But you see that there is a bijective mapping between these two and these two. Okay, that's the idea. And to explain the identity, I just quickly recall the q numbers, the q factorial, the q binomial coefficient, and the q multinomial coefficient. And if anybody doesn't know, please ask. And our theorems are the following. So if you sum over wk greater than for the quin, you get this prefactor of q, some q power, times a multinomial coefficient, q multinomial coefficient times a q binomial coefficient. And they don't absorb because this is L and this is L. You cannot combine them. And similarly, if you take w less than or equal to, you get L and L minus 1. Okay, so it all works out rather beautifully, and we use the standard fact that the inversion generating function of words is a q multinomial coefficient, and then we have to use q series identities like the q mode identity also. Okay, so in the last minute maybe, or -1th minute, let me just mention some open questions. So as I said, the two definitions of inv and quin were tantalizingly similar, but we don't see any obvious bijective proof. And here's a refined identity, which we don't know how to prove. So suppose you say that two tableaux are row equivalent if every row of one is a permutation of a row of the other, of the same row of the other. Okay. And now if you let box sigma be the equivalence class of such tableau, then we believe that t to the quin of q to the match is the same as t to the in. Okay, so even this we cannot prove. If we could prove this bijectively, then we would of course have a proof of the big thing. But even this we don't immediately see how to prove. And as I said, our proof on words was a proof of existence of bijection. We don't actually have a bijection, and that would also be interesting. Okay, so let me stop with this, and thank you for your attention. And Gaurav already did it for me, so I wanted to thank Venkatesh also for organizing.
Any questions? Questions or comments?
Yes, the combinatorial formula which you have, does it extend to skew shape?
Oh, combinatorial formula for
Macdonald, for the modified Macdonald polynomials.
Ah, I never thought of that. Okay, but
one could experiment at least.
No, we did not think of that. But does HHL's formula, does anybody know if it has does it extend to the skew case? Does anybody know in the audience?
Well,
do you know, Michael, if it extends?
no, I don't know now what you.
Okay, yeah.
What is the definition of modified Macdonald for skew shape? Is it just the pathetic shift of the usual? Well, I don't know what the definition of such an object that we would be trying to do
okay,
is.
so maybe I'm confusing it with the standard theory where you have a combinatorial formula in terms of tableau, but of course this is now different. So I don't know.
You mean P for P lambda mu, lambda slash mu?
Yes, for P lambda, of course, it makes sense. I don't know if this question makes sense here, this setting.
No, we never thought of it.
But of course, you could start with different tableaus, like skew shape.
Yes, we could potentially start with.
Yeah.
But we did not experiment with it. Yeah, that's true.
May I ask a question? So about the probabilistic realization. So you gave this model for the modified Macdonald polynomials via these processes. Is it a complicated theorem, so hard theorem? So I mean, how one would prove this?
Right. So as I said, so we followed the same strategy as for Ferrari and Martin. So what the idea? Okay. So what we want to do? Okay. So let me go back. Give you the example. Yeah. So let's look at this example. Okay. So we want to say that the stationary probability of this state is proportional to this. Okay, so if you multiply out by this denominator, I mean, we are only talking about polynomials now. So what we want to do, or one strategy of proof, is to construct a Markov chain on a larger space, which projects in the sense of Markov chains. It's also called a lumping, such that there are for this example, there are two objects that project onto this state, and the weights in that enriched Markov chain, the stationary distribution of that enriched Markov chain is monomials, and there is one monomial, one state with monomial x1 to the 4, and one state with monomial x1 cube x2, which projects onto this state. Right. So if we can do, this is one standard strategy of proof, to construct a larger Markov chain, where you know, or you can prove, that each state has a stationary distribution which has one term, which is a monomial. Then you get this for free almost by summing. So the projection of Markov chains guarantees that the stationary weight of this is going to be proportional to the sum of all the things that you get by projecting. That's the strategy of proof. So that's what Ferrari and Martin used, as I said, in the multispecies ASEP, and we can follow the results.
And from the side of modified Macdonald, you use the HHL formula, or how do they work?
No, we don't. No, we are not using any formula. I mean, this is R t to the quinv, not inv.
Okay.
So,
but I mean, when you compare the probabilistic part and the combinatorial part, so you have somehow to identify the result with the modified Macdonald. So what is what definition are you using?
No. So we are using our definition, because if I set q equal to 1, this sum over all fillings with entries in 1 through n is going to give me exactly this. So the sum of all things is going to be 1 for free for me, because we have.
Okay, I see. Thank you.
But as I said again, I repeat that this is not the ultimate, because we don't have a q. So we don't. This is not optimal yet.
So Arvind, this is maybe more of a philosophical question, because we have the HHL formula, and now we have a second one that looks quite similar, but you tell us, well, it's really quite different in the sense that it's not easy to transform one to the other. It's just you use the same proof approach. Why should there be 2, or are there 10, or are there, I mean, where do these different formulas come from? So, rather, because it seems like you cook up a reasonably non-trivial statistic, and then you just check that all these conditions are satisfied. But that doesn't really explain, right, the origin of the formula.
Right, so that is correct. So somehow, okay, I mean, I'm biased, of course, but I think our statistic is more natural because this quin you can really interpret in terms of the multi-species Q. You can really see it as when so you have this multi-line process, you have to somehow project it, and you see this quin is really giving you the number of refusals of in queuing theory. So refusals of service, what I call. And so this complicated arrangement of three things somehow seems more natural to me. Right? And it's natural to ask if such a thing also holds for their HHL's things, but we could not see any such process. But of course, to your original question, I don't know. I simply don't know. I mean, why would? Yeah, there could of course be any number of formulas, but somehow this seems to be more natural, and this seems to be something that they could have also discovered. I mean, if they had just twisted their thing around, maybe they would have found it possible. I mean, I don't, but yeah, I really don't know why one would expect. Somehow this triple of cells seems to be the key thing here. So, but I don't know. Yeah.
And when it comes to showing particular properties of the modified Macdonald polynomials, would one work better than the other? So are there particular properties that you can easily infer from your formulation, for example? Or
Yeah, that's a good question. I don't know. I mean, in terms of our strategy of proof, it's certainly much harder. But we followed HHL's proof because they already had it. I mean, I don't know if we might have found a simpler proof if we did not have it. But
yeah, but
yeah,
my question is not so much about the method of proof, right?
Yeah.
Once it's done, and we can accept that this is correct. But now you have your formula. Can we use it to infer properties of the modified Macdonald polynomials that were, I guess, less clear previously? Or
I don't know. I guess I have not done a systematic study of these things, but maybe yeah, it might well be possible. I just one way or the other.
Excuse me, may I ask a question?
Yes, please.
Yes. Yeah, about well, this slide that you show here, your result on the TAZRP. Does this result also allow you to compute some physical quantity in an easiest way or an easy way or whatever?
We have not
average
tried.
current.
Yes, we want to try. Yes, that is part of our plan to try compute things like densities and currents. Yes, we're going to try. I mean, yeah.
Okay.
But we do have some recourse, right? Because we know that the. Oh, actually, maybe we already know the density. Because
The density are fixed.
the bottom row, and we know. Yes, we know this actually. So here is another nice property which is not obvious at all. So if I take my partition diagram and I chop off the bottom row, okay, then I get another diagram of a smaller partition, and that somehow naturally sits inside this. So the weights sort of fit in nicely. So I believe densities at least we will be able to get almost for free. But currents may be harder. But yeah, we're planning to look.
But, sorry, but what do you mean by densities? I mean, the number of particles are fixed, so the density are fixed, no?
No, site densities. So,
site density, okay.
Yeah.
Okay.
Am I saying something stupid? No. Sorry. Site densities are, are
the profile, okay.
Yes. No, but I'm saying, no. Okay. Sorry. It's correct. The inhomogeneities are there, so it's not translation invariant.
Okay.
Right. So I do get densities. Yes. I will get site-wise densities. I don't know about the current. But yeah, that's certainly.
Okay.
Any further questions or comments? Okay, so if not, I want to again say thank you very much for all the organizers, Arun Ram, K. Raghavan, Venkatesh, and Vishwanath, and we thank all the speakers of the conference, and hope we meet again very soon. So,